Hey, you ever feel like you're right on the edge of understanding something huge, something really revolutionary?
Yeah, like something that could just change everything about technology.
Exactly.
Yeah.
Like there's this incredible power sort of hidden under the hood of our regular computers.
hmm
Well, if that sounds familiar, you're definitely in the right place today. We're diving into quantum computing.
That's right. And it can sound, super complex, maybe even a bit sci-fi.
Totally. But we've got some great insights lined up based on work from experts at IBM and some clear explainers from What Is.
And our plan really is to break it down, give you the essentials without getting bogged down in like heavy physics equations.
Yeah, exactly. Our mission today, cut through that complexity, get you a solid grasp of what quantum computing is and importantly, why it's such a big deal. All pretty quickly. Think of it as your fast pass to the quantum realm.
Let's do it.
Okay, so let's get straight to it. In simple terms, what is quantum computing? How is it different from, say, the laptop I'm using right now?
Okay, so your laptop, that's a classical computer. It works with bits, and bits are pretty simple, right? They're either a 0 or a 1, on or off.
Right, binary. Got it.
Quantum computing, though, it plays by different rules. It uses quantum mechanics, and instead of bits, it uses qubits.
Qubits, okay.
And here's the wild part. A qubit doesn't have to be just 0 or 1. It can be 0, it can be 1, or get this, it can kind of be both at the same time.
Hold on, both at the same time. That's a bit mind-bending.
It is. And that fundamental difference, that bothness, lets quantum computers tackle certain types of problems, really complex ones, way faster than even our best supercomputers today.
Way faster. Like how much faster are we talking?
Well, imagine a problem, maybe something in drug discovery or material science. That would take a classical supercomputer literally thousands of years to churn through.
Okay. Yeah, that's basically impossible then.
Right. A quantum computer, hypothetically, might solve that same problem in minutes.
Whoa! Okay, thousands of years down to minutes. That's a game changer.
Absolutely.
Yeah.
Now, it involves specialized hardware, quantum hardware, and completely new types of algorithms, quantum algorithms. It's definitely still an emerging field, lots of development happening.
But the potential is just massive.
Huge potential, yeah.
So this qubit,
Mm.
this is the key then. How does that both 0 and 1 thing actually work? Can you give me an analogy maybe?
Sure. Think about flipping a coin while it's spinning in the air before it lands. Is it heads or tails?
Well, neither yet.
Oh,
Or kind of both, I guess,
yeah.
until it lands.
Exactly. It's in that uncertain state. That's kind of like a qubit in superposition. It exists as a combination of 0 and 1 simultaneously.
Superposition. Okay, I like the spinning coin.
And this ability, this superposition, it's what gives quantum computers their edge for certain jobs. See, if you have, say, 2 classical bits, they can represent one of 4 possible combinations, right? 0, 0, 0, 1, 10, or 11.
Right, one at a time.
But 2 qubits in superposition, they can, in a sense, hold information about all 4 of those possibilities at the very same time.
So they're exploring all the options at once.
Kind of, yeah. It allows them to process vastly more information, and it scales exponentially. 3 qubits handle 8 possibilities, 4 handle 16, and so on. It grows incredibly fast.
Okay, that's powerful. But eventually you need an answer, right? Like a definite 0 or 1. How does that happen?
That's a really important point. When you finish the quantum calculation, you measure the qubits, and the moment you measure them, that superposition collapses.
So the spinning coin lands.
Exactly. It snaps into a definite state, either 0 or 1, just like a classical bit. The magic, or rather the cleverness, is in the quantum algorithms.
How so?
Well, they're designed to manipulate the probabilities before that measurement happens. They use quantum effects to increase the chance that when the qubits do collapse, they collapse into the state that represents the correct answer to your problem.
Okay, so you're steering the probabilities towards the right outcome. You mentioned superposition. Are there other weird quantum things happening?
Oh, yeah, definitely. Besides superposition, another really key one is entanglement.
Entanglement.
Yeah.
Sounds spooky.
It kind of is. Imagine you have 2 qubits, 2 of our quantum coins, and they're entangled. This means their fates are linked in a really, really deep way, stronger than just random chance.
How strong?
So strong that if you measure one entangled qubit and find out it's, say, heads, you instantly know the other one must be tails, no matter how far apart they are.
Instantly. Even miles away.
Instantly. It's this bizarre connection that Einstein famously called spooky action at a distance. It allows for incredible correlations.
Wow. Okay, that is weird. What else?
Then there's decoherence. This is basically, well, it's the enemy.
The enemy? Uh-oh.
Yeah. Remember how delicate that superposition state is, like the spinning coin? Decoherence is when something from the outside world, like noise or vibration, bumps into the qubit.
And it stops spinning.
Pretty much. It causes the qubit to lose its quantum bothness and just become a plain old 0 or 1 before you want it to.
Oh.
This messes up the calculation. So protecting qubits from decoherence is a huge engineering challenge.
Wow.
And finally, there's interference. Think about waves in water. Sometimes waves add up, making a bigger wave, and sometimes they cancel each other out.
Right. Constructive and destructive interference.
Exactly that. Quantum states can interfere in a similar way. Quantum algorithms use interference to amplify the probability waves pointing towards the right answer and cancel out the waves pointing towards wrong answers. It's like it helps zero in on the solution.
So you've got superposition for exploring possibilities, entanglement, linking things up, interference guiding the result, and decoherence trying to mess it all up.
That's a pretty good summary.
Okay, so harnessing all this strangeness. How do you actually build one of these things? What's at the heart of the machine?
Well, the core is still the qubit. That's the fundamental difference. But how you make a qubit, there are several ways. Scientists can manipulate individual quantum particles.
Like what kind of particles?
Things like photons, particles of light, or electrons, or ions, which are atoms with an electrical charge, even whole neutral atoms. Or they can build tiny engineered systems that behave like quantum particles, like superconducting circuits.
Superconducting circuits. And I've heard they need to be kept ridiculously cold. Why is that?
Yes. The cold, that's mainly to fight decoherence, the enemy we talked about.
Right. Stop the outside world interfering.
Precisely. Those quantum states are incredibly fragile. Any thermal energy, any vibration can knock them out of whack. So companies like IBM cool their quantum processors down to, well, near absolute zero. We're talking temperatures colder than deep space.
Colder than space. Wow. How cold exactly?
IBM uses coolant systems that get down to around 25 millikelvin. That's about minus 459 degrees Fahrenheit, just a tiny fraction above the coldest possible temperature.
That is seriously extreme, just to keep the qubit stable.
Yep. Minimize that environmental noise as much as humanly possible.
And you mentioned different ways to make qubits superconducting ones, ions, photons. Are they all basically the same, or do they have different strengths?
Good question. No, they're not all the same. They have different pros and cons. Superconducting qubits, for example, are relatively fast for operations. Trapped ions, on the other hand, tend to hold their quantum state for longer. They have better coherence times.
Okay.
Then you've got quantum dots, photons, neutral atoms. Researchers are exploring all these avenues. The best type might depend on the specific problem you're trying to solve. It's still an active area of research, figuring out which architectures are best for which tasks.
So let's recap the big difference then. Classical computer.bits, 0 or 1, does things step by step. Quantum computer.qubits, 0, 1, or both, superposition, uses entanglement and interference to explore possibilities sort of in parallel.
That's the core idea, yeah. Classical is deterministic, follow the steps, get the exact answer. Quantum is probabilistic. It uses interference to boost the odds of finding the most likely correct answer.
Most likely. So you might have to run it a few times.
Often, yes. You might run the quantum algorithm multiple times and look at the distribution of results to be confident you found the right solution. It's a different way of thinking about computation.
Which means quantum computers aren't going to replace my phone or laptop for, like, checking email or watching videos, are they?
Haha, no, definitely not anytime soon. Probably never. Classical computers are fantastic for most everyday tasks. They'll remain dominant. Quantum computers are specialized tools.
For those really, really hard problems.
Exactly. The ones that are just intractable for classical machines, even supercomputers. Think about complex simulations or optimization problems with a staggering number of variables.
Okay, so when does quantum really shine? What kind of problems make you say, this is a job for a quantum computer?
It's usually problems where the underlying system is quantum, or problems with immense combinatorial complexity, like simulating how atoms behave in a molecule to design a new drug or catalyst.
Why can't a supercomputer do that?
Well, even a moderately sized molecule involves complex quantum interactions between many electrons. Trying to track all those possibilities classically just overwhelms even the biggest supercomputer's memory and processing power. It scales incredibly badly.
But a quantum computer.
Because it operates using quantum principles like superposition and entanglement, it can create a computational space that sort of naturally mirrors the quantum system you're trying to study. It's like fighting fire with fire, or rather, quantum with quantum.
Okay, that makes sense. Using quantum rules to simulate quantum rules. What other areas?
Oh, potentially loads. Material science, discovering new materials with specific properties, financial modeling, optimizing complex portfolios, logistics, finding the absolute best routes for shipping networks, even things like cracking certain types of encryption.
Ah, yes, I've heard about that. Shor's algorithm.
Exactly. That's a famous quantum algorithm that could, in principle, break much of the encryption we rely on today. That's a big driver for quantum research, both for breaking and creating new quantum-resistant encryption.
So defense implications too.
Yeah.
It sounds like it could touch almost any complex field.
Potentially, yes. Pharmaceuticals, chemistry, machine learning, AI, supply chain optimization, maybe even climate change modeling. Anywhere you have massive complexity and interactions.
Where are we right now, though? Are these things actually solving these problems yet, or is it still mostly theory and potential?
We're kind of in an exciting middle ground. We're moving beyond pure theory. Researchers are building larger and more stable quantum processors. They're developing better ways to correct errors, remember decoherence.
The enemy.
Right. Error correction is crucial for reliable quantum computation. We're starting to see demonstrations aiming for quantum utility.
Quantum utility. What's that?
That's basically the point where a quantum computer can reliably solve a practical problem faster or better than you could with brute force classical simulation, even if it's not the absolute fastest classical method overall. It's a stepping stone towards quantum advantage. That's the bigger goal, where a quantum computer definitively outperforms any possible classical computer on a specific useful task. We're not quite there across the board yet, but progress is being made fast.
And how do they measure that progress? This is like a speed rating?
It's tricky because speed isn't the only factor. They use benchmarks like quantum volume, which tries to capture both the number of qubits and how well they work together without errors. There's also CLOPS, circuit layer operations per second, trying to measure speed more directly. And people are focused on scaling up.
Scaling up the number of qubits.
Yes, but also making them better quality with less noise and better connections. IBM, for example, has roadmaps aiming for thousands of reliable, error-corrected qubits within the next decade or so. And it's not just the processors, it's scaling the cooling systems, the control electronics, the cost, the energy use.
So there's a whole ecosystem challenge. Hardware, software, algorithms.
Absolutely. And developing the software is huge too. Tools like IBM's Qiskit were making it easier for people to actually program and run things on quantum computers. It's becoming more accessible.
Which brings me to my next question. These things sound incredibly expensive to build and run with the cryogenics and all that. Is this tech just for, like, giant corporations and government labs?
Well, building your own quantum computer, yeah, that's still extremely expensive and complex. You can buy small desktop ones, but they have very few qubits, more for educational purposes.
So how does a regular researcher or a smaller company get involved?
That's where the cloud comes in. Quantum as a service, or QI.
Yes, like size, but for quantum.
Exactly. Major players like IBM, Google, Amazon, Microsoft, D-Wave, Quantinuum, Xanadu, they've built quantum computers and allow people to access them remotely over the internet.
Ah, so you don't need the fridge in your office.
Nope. You can write your quantum program, send it to their cloud platform, run it on their actual quantum hardware, and get the results back.
That makes a huge difference.
It really does. It lowers the barrier to entry enormously. It makes it much more cost-effective. You only pay for what you use, and you get access to the latest hardware without having to build it yourself. It's really accelerating research and exploration.
Okay, well, this has been really illuminating. It feels like we've covered a lot of ground pretty quickly.
We have.
For me, the big takeaway is this isn't just a faster version of today's computers. It's a fundamentally different way to compute, tapping into these really strange quantum rules.
That's the heart of it. It tackles problems differently, using superposition and entanglement to find solutions in ways classical computers just can't.
And while it's still early days, the progress seems real. Hardware's getting better, software's developing, people are accessing it through the cloud.
Exactly. It's a revolutionary field, no doubt about it, and it's moving from pure research towards potential practical applications. It's going to be fascinating to watch.
So maybe a final thought for everyone listening. Think about your own field, or just areas you're interested in. What are the really tough nuts to crack? The problems that seem completely impossible right now.
Mm-hmm. The grand challenges.
Could quantum computing, maybe not tomorrow, but someday, hold the key? It's kind of mind-boggling to think about what might become possible. Maybe check out some of those CAIAS platforms, see what people are trying.
Yeah, the quantum revolution is definitely underway. It's an exciting time.
It really is. Thanks for breaking it down for us.
My pleasure.